First of all, feel free to tell me if my voice is not loud enough. Also tell me if I'm going to be on the way as I write in the blackboard or if I'm putting myself in front of the slides, because I'm going to try to alternate between the two. You know, this is a lecture on relative navigation, and as part of Microsat engineering, it is a kind of follow-up from the lecture that Professor Guo gave to you already. The lecture from Professor Guo was on AOCS, and you know that AOCS is mostly about the attitude, the orbit, control system. And in that part, the control word is quite the main one, right? In this lecture, I want to dig a bit more into navigation, so try to deepen a bit more the guidance, navigation, and control aspects, and go a bit far beyond the control system itself. We used to put some learning objectives here, so I was struggling a bit on how to summarize it. I think the main important things that we can expect from today's lecture are the description and understanding of relative navigation scenarios, for sure. Then the metrology part, which is, in my opinion, what really characterizes different missions. The sensors you have are going to play a huge role when I try to estimate something in the navigation. Principle of filtering techniques, that's going to be quite important. We're going to manage to tackle that problem a bit, still from an high-level perspective. And then we will try to dig a bit more into a very specific system. It will be an optical system, actually the topic of my PhD, and we will try to see what the main steps are throughout the estimation process. Again, very stupid slide, but it kind of makes sense to relate GNC and EOCS given the previous lecture. Guidance, navigation, and control means that you're not only interested in controlling something, you also want to know where you want to go and where you are when this information receives your onboard computer, right? So it goes much more beyond control. In the specific application of today, we want to tackle the problem of GNC and navigation in particular for mostly two types of missions. One is rendezvous and docking. The other one is formation flying. And I actually put two different kind of labels attached to those missions, which you can see there in red, cooperative and uncooperative. Now, you're going to see during the lecture how this distinction will make sense. For now, we can just consider an uncooperative spacecraft as a spacecraft that doesn't aid at all our navigation, whereas a cooperative one has some sensors on board or some other means or ways of helping the estimation, right? You can expect in a formation flight mission, you have active satellites cooperating with each other, so they're going to be most of the time, if not all the times, cooperative. However, when you're doing rendezvous and docking with a debris or a satellite you want to refuel, you cannot take for granted that that satellite is going to be cooperative. Right? So this is in a nutshell the distinction between the two. Again, still in the introduction part, when we focus on GNC, as I said, we can focus on the guidance, the control, and the navigation. But when we're talking about relative navigation, we want to skip the guidance and control part and focus entirely on the question, where am I? Right? And then when you ask the question, where am I, you can ask the question, where am I with respect to a satellite, where am I with respect to an Earth fixed system, or many other reference systems attached to any other type of object. You can expect, since today's lecture is on relative navigation, that what we're going to be tackling is the navigation information between one or more satellites with respect to each other, right? So it makes sense when you're trying to understand where am I to relate your information to the object of reference, the satellite in particular, right? So this is a kind of recalling something from many previous lectures that you had. If we have the Earth Center Inertial Reference System, we have PCI frame, and then we have the orbit of a certain object, so we can consider this to be the orbit of our satellite. And then we have other objects. It can be another satellite information, it can be a target that we want to deorbit, and so forth, right? So we don't care about the navigation solution of this point with respect to this system, because this is not going to help our relative navigation. We want to know the information of this point with respect to this point. So this is going to be our reference point. We can say satellite 1, and this is going to be, in our case, for example, the target. So we need to create a reference system attached to the satellite number 1. And this is, as you know, the local vertical, local horizontal system. And I'm defining it now because we're going to use it all the way during the lecture. So as you might recall, we just take the radius of this satellite with respect to the Earth. This is going to be the first versor. So it will be nothing more than the radius of the satellite divided by its north. Then we define an additional axis. I will call it axis K. And K is the vector product of the position and the velocity. So it will be in the same direction of the angular momentum of the orbit. And then we will define J as K vector product I. So what happens is that if you look, for example, at your target from the spacecraft, and you're in a circular orbit, what you're going to see is that your long track direction is represented by this vector. Your radial direction is represented by this vector. And your cross-track direction is represented by this vector. So you basically have the satellite in the blackboard, and you're looking right in front of it, right? This is how we define the local vertical, local horizontal frame. Let me just change the slides quickly. I think I took the ones. Okay, sorry. Yes. Now, when you define the local vertical, local horizontal frame, what you want to do is to represent the information. And from a navigation perspective, the information that you want to represent is, first of all, the position. It can also be the attitude, because when you're approaching a satellite, you want to know exactly how you are oriented, right? And you need to find a way to propagate this information in this reference system. And this is, as you know, what the Cauchy-Wilshire equation do. You basically start from a certain guess x0, and this could be the position and the velocity of your target, and you want to know the position at a certain instant t, right? And you have this map, which basically transforms your initial state into the state after that. Now, as I said, we are interested in attitude and position. The Cauchy-Wilshire equation propagates only position and velocity. So if you want to also propagate the attitude, you need to use the Euler equation for the dynamics, then the kinematics for the Euler angles, the quaternions. We're going to see later. That's not important for now. But the important thing is that you can express this in a linear way by saying that the x, step k plus 1, is equal to a certain state transition matrix that multiplies the state at steps k, right? So in this way, you just propagate your state. This matrix, I think I try to represent it here, for the Cauchy-Wilshire equation is represented there, and in terms of relative orbital element there. If you're not familiar with the relative orbital element, I am sorry that I'm not able to tackle that specific problem now. You can approach me later, or I can recommend you some specific papers that tackle it. But in a nutshell, the important thing is you do propagation, whether of the relative orbital elements or of the Cartesian state, right? What you also have to do when you do propagation, and you're going to understand a bit why, is to also propagate statistical information associated to your propagation, right? What you usually have is a certain state, which is x, and then you have a covariance associated to it, right? So you know, this is what I'm propagating, and the uncertainty of my propagation is represented by a specific matrix when you're dealing with linear states. In this case, what we can also associate to the x to the k plus 1 state is also a certain p matrix. From now onwards, this will be our covariance matrix. And the p matrix at step k plus 1 is also propagated with the same transition matrix. So you have here p at step k, and then the transposed. So this is how you propagate your covariance. So at this step in time, you have covariance and state. Now remember, your propagation might have some error. It might be that you're not accounting for perturbations, or the dimensionalization error is not negligible. So you always have to account here some statistical uncertainty of your covariance. It doesn't come only after this term, but it also has this specific Q term. And this is how you call the process noise. So this is the noise that comes from the propagation when you don't have a perfect system. Sorry, when you don't have perfect propagation, right? So again, still in the introduction, but this is what you want to do when you want to propagate a specific state, right? Now, there is another thing that we need to remember. I think I can delete quickly this part here. This part here. Imagine you have something that varies in time. You start from a certain x0 and you propagate. So at each time step, you have a certain value for the x state. Right? Now imagine this is time t1 and this is x1. x1 is what my propagation state is telling me. Remember, we're still talking about navigation. So this information would be my state in terms of relative position, relative attitude, velocity if I'm interested, angular rate, whatever I want to estimate. And then at this step, I have this state, and I'm not that sure how accurate that state is. I have the P matrix telling me how accurate it is, but I'm still not that sure whether this is the final state that I want. And then imagine that at the same time, T1, you also acquire some measurements. So you have some sensors on board which are telling you, in my opinion, this is where you actually are. So the sensor might be telling me, you say that you're here, but I'm telling you that you're here. And we can call it XM, which means the state that comes from the measurements, right? Now the question is, do I trust my propagation or do I trust my measurements, right? And the answer is you don't trust any of the two 100%. You need to find some kind of balance between what the measurements are telling you and what the propagation is telling you. So ideally, you want to play around in this line and try to find a value here which is the most optimal. Right? And this is when exactly we get into navigation. This is exactly the moment in which you start dealing with navigation filters. You don't rely only on your propagation with those Cauchy-Wishart equations and so forth, but you account for some measurements coming from your environment, right? Now, in the navigation filter, we can summarize the steps in two main ones. As I said, and this is a bit redundant, step number one is prediction. And prediction is just a synonym of propagation. So you propagate your states. And now you try to do this, to slide around this line. Now, how do you do that? We can try to consider that together. We will call this step of playing around that line correction. And we will try to represent it here in a formula that we will use later on when we tackle the relative force estimation and relative navigation. So for the correction step, we have to estimate the step at x k plus 1. And what we have is the state at k plus 1 from propagation. So from step 1. Right? So we need to add some term to make sure that we find the optimal state. Right? As I said, this additional term that we put comes from the measures. Right? So it has to make some sense that we put some measurements here. We can imagine that if we get the measurements and we have a mathematical expression that relates our state vector to the measurement, we can subtract the two values, right? So we get the measurements, we have the state from the propagation, and we just check what this state leads to in terms of measurements. In a nutshell, we just take the measurement z and we subtract them with a certain function h, which maps the state that we propagated to an analytical representation of the measurements. Right? This is just a very quick introduction on how a navigation filter works, and I'm quite sure that the majority of you knows a lot more than this now, but I think it makes sense to kind of go through and refresh a bit our minds. So this one is telling me how far am I from the measurements if I rely on x1. Now imagine we leave it as it is, and we just say this is our equation for the correction. And now we consider a situation in which the measurements are telling me that I'm here, but they are incredibly noisy and incredibly wrong in that information, right? So we don't really want to rely on this equation only, because if the measurements are wrong, or statistically speaking, not accurate enough, I'm going to diverge from a solution that probably was even better just with the propagation. And this is why I need to come here from some gain matrix that kind of weights or balances this information compared to this. And this is where the Kalman gain comes into play. So the Kalman gain is a matrix that tells me how much they trust this term called residuals. So the better the measurements are, the larger the K matrix will be, and the more I will need to correct my initial propagation. Conversely, if the measurements are very inaccurate, the K matrix will capture that, and it will tell me, don't listen to the measurements because they are not accurate. So this matrix will be very low, and the contribution of the measurements to the propagation will be almost negligible. So this is the kind of way, with the K matrix, we play around this line, and we find the optimal value. Right? So this is what we refer to as navigation filter, and in the specific to a Kalman filter. There are a variety of filters that you can use, but for lecturing purposes, I think the Kalman filter is the best one to really capture what's going on when you're trying to find your estimates. And now, again, we need to remember that we're not here for an introduction on the Kalman filter, we're here for relative navigation. So what we need to apply it to is the relative estimate between two or more spacecraft. So what are the measurements when you have this scenario? We basically have a propagation model, Cauchy-Wisher equation, relative orbital elements, and then we have the measurements. Now, what really distinguishes a mission from another is the sensor you put on board and the measurements you get from the sensors. You might consider a formation flight mission or a rendezvous mission both applying the Cauchy-Wisher equation for the relative motion, but having a completely different set of sensors. So what we call metrology, the number and amount and type of sensor you have, is the one that plays a crucial role when you have to distinguish between missions. And this is why now we're going to start tackling this problem. So what I wanted to do now is to analyze. I wanted to analyze what happens in different missions based on the sensors you use. So we're going to kind of rely on this equation here and see what happens. Remember, where am I with respect to my spacecraft? Where am I in terms of position? Where am I in terms of attitude? Also, how fast I'm going, how fast I'm rotating, and so forth. So the measurements are related to this information. And it makes sense that in a formation flight mission, rendezvous mission, the sensors that I'm going to use will return information on the position and the attitude, mostly, right? Now, the first step is to analyze position information. And the first kind of straightforward answer to which sensor I'm going to use is the GPS, right? Remember, you might know how the absolute GPS works, but you also have to remember that you're now going to apply the GPS for relative motion. So you need to find a way to return the information of the GPS into a relative information, not an absolute one, right? So let's try to have a quick recap on how the GPS works. We still have our Earth here. We still have an orbit, and then we can start from one single spacecraft. So we will tackle absolute GPS first, and then we move to the relative one. So we have one spacecraft. This will be called spacecraft K. And then we have the constellation of GPS, and I will represent here only one of them. I would say I equals 1, but there will be more than one in the constellation, depending on the constellation that you use. The metrology that we use, the one that we will feed here later, is the metrology associated to the relative range between my satellite and the GPS, and the other satellite and the GPS. And then we do some subtraction and we find the relative force. So we need to start from here and from a single satellite. What the GPS will do is, the GPS will send signals all around space, and there will be a transmitter here on the satellite capturing that information, right? Now, what the GPS is sending is what is called the pseudo range number. Again, I know some of you follow some courses on that, some of you did not, so it's good to quite recap on that. So imagine you have this signal, it can be a sequence of zeros and ones. And this is the transmitted from the GPS. And then with our receiver from our spacecraft, we receive another signal which is shifted. So it would be, for example, something like this. right? And if we can compute this shift, we can relate this shift to the difference in time between when the GPS sends the signal and when we receive the signal, right? So this shift is a time information. And if you apply the simple rule that the velocity of light times delta t equals a certain range, we can determine the range between my GPS and my satellite and the GPS I by computing the delta t and multiplying by the speed of light. Now, this information here, as you might know, is called pseudo range and not range. And the reason why it's called pseudo is that it doesn't really make sense to call it range. If there is noise in t or in any other parameter, which we will understand and discuss later, this doesn't really tell you how far you are, but it tells you something which is affected by noise. That's why it's called pseudo. It doesn't really is the range. So this pseudo range is related to delta t, but we need to account for another term here, at least one, and this term is a bias. The reason for accounting for this bias is that, as you know, the GPS have very accurate and precise atomic clocks, which are synchronized, but my receiver does not. So I can compute this delta t, but I'm not really computing this delta t in the same reference, right? So I will be asynchronous with respect to the GPS, and I will have some bias here, right? So this is the equation, and now, again, referring to the Kalman equation, we need to find a way to reconstruct the position of our satellite with respect to the GPS from this. And this is actually not very difficult if we consider that this is a absolute value, not a vector, of the distance. So this will be the square root of the x, y, and z components, right? And this will be the absolute position of my satellite, this is sk, minus the x of the GPS number I, squared, including the y and the z components, right? So if we wrap it up, we see delta t, we measure. The speed of light, we know. The x, y, and z components of the GPS number I, we know because together with the pseudo range number, the GPS will also send me the ephemeridis and its absolute position. So that information is included in the transmitted code. What we need to estimate is basically the x, y, and z components of the satellite, still for the absolute position, which are x, y, and z, three unknowns. And then we have the bias term, which we also don't know, which makes it 4 unknowns. And this is why when you want to estimate your position, you need to use at least 4 GPS satellites, or more than 4 to tackle the noise, right? So we basically have a way of computing our absolute position with respect to the satellite. Now, what happens when you want to compute the relative position? We can imagine this is the navigation system on board one of my satellites, right? And I have here at least 4 GPS satellites or more. I have here my receiver, and I'm taking all this information, right? This is, I will call this nav main because it's on the main satellite, for example, in a formation flight mission, let's say. And then we have the same 4 GPS, which are transmitting the same information to the receiver of the second satellite, right? Now, the second satellite can process this information and send it via an intersatellite link to the main spacecraft. So now we have a task to be executed in the navigation main of the spacecraft number 1, which is to reconstruct the relative position based on measurements. My measurements come from the GPS. The GPS tells me these parameters and has this noise. So if I can incorporate this information with the information of the other satellite, I can basically compute a delta R, and that would be the measure of my relative range with the other satellite, right? Now, of course, this is not as straightforward and there are complications, but from a mathematical perspective, the principle sounds as simple as this. One main beneficial aspect of this is that the accuracies that you can receive with a relative GPS are much better than the accuracies that you can achieve with an absolute GPS. And the reason is that this equation is not complete. There are more noise terms, which I prefer to include in a slide just because it was too long otherwise. So we have the pseudo range R between satellite K and satellite I. We have C delta T, which is the real range, and then a train of noise terms, right? The first term, ET rec, that's the error due to the receiver clock bias, basically this one. And this will be filtered out if we have at least 4 satellites in the constellation. And then you have a set of other noises. One is the ionospheric, one is the tropospheric, NREC, TSAT, ephemeridis. Now, let's focus on tropospheric and ionospheric. Those two noises are noises related to the fact that light travels at different speed if it's not in vacuum. And when you have lower orbits, you cannot assume that it's perfect vacuum. So in the ionosphere and in the troposphere, there will be some different transmission of the light path, which will affect the time I will receive the signal, right? However, if these two satellites are properly close to each other, these errors of satellite 1 and 2 will be the same. So when I'm doing the subtraction of this pseudo range, both the ionospheric and the tropospheric errors will cancel out because the two satellites are experiencing almost the same atmospheric condition, right? And then we can also get to another important aspect. You see, what comes out after that cancellation is that N receiver and ETSAT are the main players of the noise. So if we design our receiver properly, and we can, in some ways, filter out the remaining satellite clock error, then we can receive a much better accuracies. And for relative motion, it was proved that you can even go down to centimeter level, which is unbelievable compared to the accuracy of meters level that you can achieve with the GPS. So if you want to navigate with one or more satellites, and you are, let's say, in low Earth orbit, using relative GPS is quite a powerful way of handling metrology and doing your estimates. Right? So if we recap, we have propagation, Qureshi-Wiltshire, and then we apply metrology from the relative GPS, and we refine our estimates. However, there is a problem. I think this is not very important. There is a problem in terms of the orbit geometry you're going to be dealing with during your mission. If this is the Earth, and we have the GPS constellation, well, of course I'm not going to represent all the satellites, but let's say few satellites are going to be here. If my orbit is low Earth orbit and also circular, what will happen is that at almost every point in time in my orbit, I look up, and I see a GPS constellation. So I can get my information, I can get my metrology, I can estimate my state. However, imagine that I'm into a very highly elliptical orbit. Right? So when I'm at the perigee, I can still rely on many satellites in the view from the GPS constellation and get the proper measurements. But when I'm close to the apogee, something different happens. And we can understand what happens if we try to zoom into what every GPS satellite does. What each GPS satellite does is to look down at Earth, because that's what they were designed for. So if this is the Earth, and this is my GPS satellite, the satellite will look down, and it will have an omnidirectional antenna. It will have a certain pattern, so it will be, for example, with some lobi, but it will be within a cone of, if I'm not mistaken, around 20 degrees. So if you have a very elliptical orbit and you are far from Earth, you're going to see the back of some of the GPS satellites. And you might end up in a situation in which you don't have the 4 you need for the navigation solution, right? So the GPS is cool, and the GPS can work down to centimeter level, but it cannot be used for any orbit that you have. If you have eccentric orbit, consider to use the GPS maybe in the perigee, but not in the apogee. And for the apogee, you need to find something else, right? If we still stick to using RF metrology, what would be the other option? Now, the other option would be to have a transmitter and a receiver on my spacecraft, and one transmitter and one receiver or on the other spacecraft, so that they can communicate with the other spacecraft if that spacecraft is cooperative, and take out of the equation the GPS constellation, right? So what you basically do, again in summary terms, is to send a signal from your satellite number 1, have it reflected or retransmitted from your satellite number 2, and then compute the phase shift. So you basically do what you did with the GPS constellation, but without GPS. Now, you see there is the range which we can extract from this phase shift, and the range is equal to the phase shift times lambda divided by 4 pi, right? When you look at that equation, you can see one important thing. You can see that if 2 times the radius is larger than lambda, I have an ambiguity. And I have an ambiguity because the angle spans only between 0 and 2 pi, right? So an ambiguity will occur exactly when 2r is equal to lambda, and it will continue when that term is larger, right? Now, one option. If this is really the issue, what I can do is to take lambda and put it very large, right? Because if lambda is large, it will be very unlikely that my radius will be larger than lambda. So in a way, I can play with lambda and say, I'm going to have very low frequency signal, so that the ambiguity will be tackled in some ways. However, large lambda means low frequency means low power, and so forth. So you lose a lot of accuracy in your measurements. And you have this trade-off, right? You have this trade-off in which you need to understand, do I want to use a signal with a very poor resolution but without ambiguity, or do I accommodate ambiguities but I have a very powerful signal, right? So in my lecture, we will not find the answer to this trade-off, but I think it's important to mention that this is one of the challenges that come into play. So from an RF perspective, this is more or less what you do. Use relative GPS. If you cannot use it, you design your mission so that you have transmitter and receivers. However, remember that I've been talking only at centimeter level accuracy in the best case scenario, both with the relative GPS and for this case here. Now, imagine what will happen if your mission requirement is to have millimeter accuracy. So that would be problem number 1. Problem number 2, imagine what happens if your mission requirements say that you need to estimate the attitude as well. That's also part of relative navigation. But the relative GPS and the specific configuration of transmitter receiver do not return an attitude information. Third case, imagine you need to do all these things within your mission with a satellite which is not cooperative. So no GPS receiver on the other satellite, and also no transmitter or receiver, right? So in all these 3 scenarios, we don't really know what to put in this equation. The metrology is not proper if we rely only on GPS and in general radio frequency based. This is why in space missions with certain type of requirements, we tend to opt for optical navigation. Now, optical navigation means that you get rid of RF and you use cameras, LiDARs, for example, or lasers in general. For this specific scenario, what you might get, what you surely will get, is a different accuracy, a different operational range, and also a different type of sensor. So what I want to do is to quickly mention one mission which did this transition from RF to optical, and then also start to tackle and investigate what optical sensors mean. The mission is the power-free mission. It was a mission in which we still have the Earth. I think I should not delete the Earth, it's always here. And then we have the power-free orbit, which is an highly elliptical orbit. The eccentricity is actually 0.81, which is a very large eccentricity. So what the power-free mission design is all about is to have the GPS metrology when you're close to the perigee, because you're going to see the constellation. So we're going to call this phase the relative GPS phase. and then to use optical metrology when you're close to the apogee. Now, in the proper free mission at the apogee, you need also millimeter accuracy, right? So you are far away from the GPS orbit, but you need a lot of accuracy. So you need to find some metrology which is able or capable of returning millimeter accuracy. This is why in this area here, well, we can actually do something like this, and this is a kind of unclear zone. In this area here, you start acquiring finer and finer metrology, and the metrology is optical. So you move here from centimeter level to optical at millimeter level. This is that's what you do. So there are pros and cons in all the different type of sensors. The important thing when you have yeah, sorry, please.
Yeah, maybe you're just going to say it now, but why don't you just stick with optical if you already have equipment on board?
Yes, of course. As I said, this is a specific mission, and for the proper free mission, what they had to achieve was very accurate relative position and attitude, only when you perform some specific scientific measurements. Now, for that mission, the scientific measurement can take place only when the relative dynamics is very slow. So at the apogee, you do scientific measurements, and at the perigee, you do what they call free drift. So you have two satellites in this mission. They're going to be very precisely pointing at each other at the apogee, but at the perigee, they can freely drift. You don't take any measurements. But you still want to get some measurements, at least a centimeter level, because you want to avoid collisions when they're floating around. So they could use optical here, but they don't need to execute any scientific experiment. Right? So this is why, for photography specifically, they adopted this philosophy. But in general, I mean, the main message of this example is you don't always have to stick to one specific methodology. The important thing is the transition. So you need to know what the requirements are in terms of accuracy and know exactly in which part of your orbit phase to do such a transition and change between RF and optical. So this is one specific case. The operation is quite fair. There are many other missions which use the other way around, transition and so forth. But okay, this is just an example of how you move from one to the other. Again, it's a matter of accuracy. It's also a matter of range. You can imagine your metrology sensors, they can actually be applicable in some specific scenarios and not applicable in some others. The example of the relative GPS was quite straightforward. When you are far away from the GPS constellation, you don't have any applicability of the GPS range. So what is very important when you're tackling the metrology for your relative navigation is to know exactly when that specific one is applicable. And what you usually do, and I think this is one of the most important things when you're designing a mission which entails relative navigation, is to have a graph in which you compare the accuracy with the range. The range here might be the range just between one satellite and another, or multiple satellites in a constellation. Now, you can imagine that there would be some line. This is quite an assumption. It doesn't have to be linear, but there will be a line of some separation, which tells you that if you follow this line, you will have 1% of the range in accuracy, more or less, right? So if you go above this line, maybe I should rephrase it in error. Right? The lower the error, the more the accuracy. So if you go above this line, your sensor, your metrology is not proper for your mission, because your accuracy is not good for what you want to achieve. So you always want to stay in this area here below. Now, let's think again about the relative GPS. What I told you is that you can get sometimes centimeter accuracy, or slightly above, so we can put here centimeter level accuracy. And I also told you that in general, if the satellites are not too far apart from each other, they will always